This video is going to look at what kinds of magnetic fields we can produce by currents, and this one's just going to run through some examples. So let's say I have this current carrying wire that does something like this, and then we'll make it be shielded for a little while. From there, maybe it turns into an arc, and we'll make that still a shielded arc, and then we'll start heading back a little bit. I'm going to end up looking for the field at this location, so we'll head back a little while, still shielded, and then now maybe we'll go a little bit of an arc that's not shielded, and then we'll leave on this shielded path. I'll label some distances, label some currents. Let's have this thing be 20 centimeters, and we'll have this distance right here be, that looks like maybe 30 centimeters, and in here looks like maybe 50 degrees. Something like that, that'll work out great. So we need a current. Let's go with a current of 2 amps. And now I want to start off by labeling these different pieces. I'm going to label this wire 1, wire 2, wire 3, wire 4, 5, and 6. We don't even need 6 to be, let's have that be unshielded, just to kind of prove a point anyway. So we've got this current, this one continuous current that's going to carry all the way around here. We've got these different regions where we are shielding our wire, so we're not going to get any magnetic field contributions from those. And we want to find what our magnetic field is at this location. So I'm going to say first, right off the bat, magnetic field due to 2, magnetic field due to 3, magnetic field due to 4. Those are all 0 because of the shielding. Magnetic field due to 6, that's going to be an easy one. That's also 0 because it's right in line. So it wants to spear the point we're interested in, right? This would continue to spear right through the point we're interested in. That means we get no magnetic field there. So we are left with magnetic field due to 1 and magnetic field due to 5. B due to 1, that looks like a semi-infinite wire. I am right here underneath the end of it. It goes on forever to the left. It doesn't go on at all to the right. So I'm going to get a mu naught I over 2 pi r, but I only get half of it because it's semi-infinite wire. So I get my mu naught Tesla meters per amp. My current is 2 amps over 2 pi times my distance, which is 0.20 meters, 20 centimeters, and then all that times a half. That's going to give me 10 times 10 to the negative 7th, or 1 times 10 to the negative 6th Tesla. Now, right-hand rule is going to tell me the distance, or the direction of this thing. I want to grab onto wire 1 with my right hand with my thumb pointing to the right. When I do, I see that I get a magnetic field that points in front of my wire like this, behind my wire like this, which means everywhere below here I get a magnetic field that points into the screen. That is the direction of my B1. Looking at B5, I'm going to mess with that one. I'm going to get a mu naught I over 2r. Would be if I had the full circle. I don't get the full circle. I'm going to go times 50 over 360. That's the fraction of the circle that I have. So then I'll plug in those values. 4 pi times 10 to the minus 7th Tesla meters per amp. I still have 2 amps. I'm going over 2 times the radius. The radius now is 30 centimeters, so 0.3 meters. And I'm going to multiply this by 50 over 360. When I do all of that, I end up with a field of 5.8 times 10 to the minus 7th. Or if you like, 0.58 times 10 to the minus 6th Tesla, which is not proper scientific notation, but I'm doing it for a reason. That field points, I'm going to grab onto wire 5 with my right hand, my thumb pointing in the direction of the current, and when I do, I get a magnetic field that does this, which means up here I get a field that points into the screen. So that points into the screen. Now I have all of my contributions, right? 1, 2, 3, 4, 5, 6. And now I can add them together if I want my total magnetic field. I'm going to say my B total equals the sum of my individual B fields. They are both in the same direction. They're both inward. So I'm just going to get 1 plus 0.58. I'm going to get 1.58 times 10 to the minus 6th Tesla. That goes into the screen. That is my B total. And that's actually a pretty good representative sample of how we do these problems. We take the whole system, the whole mess of whatever's going on here, break it into pieces that we can handle. Piece number 1, then we get the shielding, so we're going to break into piece number 2. I said piece number 2 was going to end right here. So I've got like a piece of wire, but it's shielded, so kind of who cares. I've got this arc, so there's the end of piece 3. I've got this piece, there's piece 4, piece 5, piece 6, and pretty much with this kind of problem, you always have very natural spots where you can break your wire into segments. So that's how I'm going to do a problem like this. Hopefully that is pretty straightforward for you.